Hello again, my friends. Welcome again to Chemistry 101. It's Ismail Badran, your instructor, and today we are going to continue with Chapter 1, Measurements. So in the last lecture, we've been talking about significant figures and how to deal with significant figures. And just to refresh your mind here in the idea of significant figures, we have here in the picture a pencil and a ruler, and we're asked what is the length of the pencil. So again, the idea of significant figures goes all back to the instrument that you're using and the accuracy of the instrument. So in the upper ruler here, we have two rulers. The first one in the top, it only gives you accuracy with one decimal place because it's divided into units of 1, 2, 3, 4, 5, and there are no increments. There are no increments between the digits, between 4 and 5 or 3 and 4. So the best reading this ruler will give you is 4 point something, right? So we are sure about the 4. It's not 3, it's not 2. So the length of the pencil is 4 point something. And you can estimate here that the length of the pencil is, let's say, 4.5 or 4.6 from the first ruler, from the top ruler. And therefore, the top ruler will give you two significant figures. The ruler in the bottom, however, it is more accurate because there are increments between the 4 and 5, and if you zoom in here, the first thing you have to do is to determine what does each line represent. So between 4 and 5 there are 10 spaces, and therefore each space represents 0.1, okay, or a tenth of a digit. And you can now say that this is actually, the pen is 4.5 something. So you are sure about the 4, you are sure the 0.5 because the length of the pencil is a little bit more than 0.5, so you will say it is 4.56 or 4.55. It's not very clear how much is it in the third place, but in this case we are getting three significant figures, so it's 4.55. So the first ruler will give you 4.5, okay, and maybe the second ruler is 4.55. So in the first ruler you are certain about this, you are not certain about that. In the second ruler, you are certain about this and this, but you are not certain about that. The number of significant figures, as we said last time, is equal to the certain plus uncertain, okay? And therefore, the first ruler will give you three significant figures. The first ruler will give you two significant figures, while the second ruler will give you three significant figures. And of course, we talked about the ways to subtract and multiply, add significant figures. I want you to please to review this question, exercise 1.4, and I hope that you have solved the practice exercise that follows this question. Okay, so today we are going to talk about two terms that are used sometimes interchangeably, but they are actually different: accuracy and precision. Some people, they say he is accurate. Or this is an accurate device, okay, and this is a precise device. So what is the difference between the two? Well, accuracy in mathematics, it means how close a measurement is it to the true value. So how close a measurement is the true value. So we need to know the true value to refer to the measurement as accurate. The precision, however, it's how close a set of measurements are close to each other. So we don't know the true value, and therefore we just judge on the measurements themselves if they are close to each other. This picture here shows you the difference between accuracy and measurement, and this is, you know, the dart game that people play all the time. And the first picture to the left here, all the dots are actually close to the true value, to the center of the board, and they are also close to each other, and that means the measurements are precise and they are accurate. In the middle picture, the dots are actually close to each other, but they are away from the true value, and therefore we can say that they are precise. So the guy who the individual who obtained these measurements, we can refer to him as precise, or the instrument is precise. But there's something wrong here. There's something wrong that the measurements are away from the true value, and this is not accurate. Of course, the third one to the right here, they are off of each other, and they are also off of the true value, and therefore this is neither precise or accurate. Here is an example. Consider the following experiment where the mass of a piece of copper wire was determined by 3 students. So we go to the lab and we ask 3 students to obtain the mass of a copper wire. So each student did the measurements twice. So student A has 1.962, 1.978. So the average is 1.970. And the students B and C, the numbers are in front of you here. Which determination is most accurate, most precise, if the true value is 1.970. So now we know the true value. We can compare the average values. So students A and B are both, I would say, accurate because they obtained measurements. They are close to the true value. But student C, of course, he's not accurate, or she's not accurate, because her measurements is away from the true value. However, if you notice that student C, actually, she brought two numbers, 2.000, 2.002. They are very close to each other. And so maybe there's something wrong with the balance that she is using. So in this case, we say student C is precise, but she might not be very accurate. To be honest with you, to judge the accuracy and precision of measurements, it needs further discussion in statistics. So there are some tests that we can do to determine the amount of accuracy or precision. But this is just a general idea of the concept of, or the difference between accuracy and measurements and precision. The last thing in this chapter is dimension analysis, and I think I have introduced this a little bit at the beginning of this course. And dimension analysis is widely used in chemistry, and you're going to use it in this course as well. It is used to convert units to each other, or sometimes to solve chemical problems. So basically what you do is you bring the given unit and you multiply it by a factor, okay? And that factor will be the conversion factor. It is basically the desired unit divided by the given unit. The given units, they cancel out, and you are left with the desired units. An example of that quickly here, if we can bring up our whiteboard. So let's say I have 2.3 centimeter, and I need to know how much is that in millimeter. Okay, that's a question. So I know that the 1 centimeter is actually is equal to 10 millimeters. We know that already. So this is the conversion factor. So what you do here is you bring the given unit, which is 2.3 centimeter, and you always multiply. Okay, and in dimension analysis or unit analysis, you don't divide, you always multiply. Okay, you multiply by a factor. Now you have two choices here. Either you put 1 centimeter divided by 10 millimeter, but that is wrong, because centimeter times centimeter, it will give you centimeter square, and that's all wrong. It does make sense here. It does make sense to put the 10 millimeter in the top and the 1 centimeter in the bottom. And you see here, this cancels out with that, and you are leaving. So 2.3 times 10 is 23 millimeters. So this is easy. Okay. Keep in mind here that what we are multiplying here, 10 millimeter divided by 1 centimeter, this is actually equal to 1 unit. And in mathematics, we are allowed to multiply by 1. What are we doing here is only multiplying by 1. So 2.3 centimeter, we are multiplying it by 1 unit, because 10 millimeter is the same as 1 centimeter. And that's totally fine. So this is called the conversion factor, or the thing you are multiplying with. Sometimes you need to multiply twice. Okay? An example of that would be, let's say there's a car that is driving at 60 kilometers per hour, and that's a speed. And I need to know how much is that in meter per second, which is another unit of speed, okay? Because kilometer per hour is not an SI unit, as you know. Meter per second, it would be maybe they are the SI units. So how would you solve this question? Well, you need to first think about the conversion factors. To go from kilometer to meter, I think it's 1,000, so 1 kilometer is equal to 1,000 meters, and that's the first conversion factor. You might also need to think about an hour to maybe 2 minutes to seconds. Okay, so there are 60 minutes in an hour, there are 60 seconds in an hour, in a minute. So 1 hour would equal to 3,600 seconds, as you know. So these are the conversion factors that you want to use to solve this problem. So you do it, the way you do it, as I said, you always multiply, okay? So you bring this given to you, this is the given unit, 60 kilometer per hour, and you multiply, okay? Keep in mind that down the road, you will provide an answer with meter per second. That's your template, okay? So at the first stage of this, you don't worry about the calculations. You just build yourself a solution template for this, okay? Or a structure or a frame for this. So first of all, I want to change kilometer to meter. So it does make sense here to multiply by a factor where kilometer is down and meter is up. But one meter is not equal to 1 kilometer. From the conversion factor, we know that 1 kilometer is equal to 1,000 meters. So that's good. The kilometer will cancel out the meter. So now we have meter per hour. So we are not there yet. We need to continue and multiply again by a conversion factor that goes from an hour to second. You see, I'm putting the hour up now, so it cancels out with that. But 1 hour is not equal to 1 second. 1 hour is equal to 3,600 seconds. So now you're good. Now you have meter per second, which is exactly what you want. Okay? So what you do here is you multiply 60 times 1,000, which is 60,000, divided by 3,600. So here we have, I think, a bunch of questions that we need to solve, and that will be the end of chapter 1. A person's average daily intake of glucose, which is sugar basically, is 0.0833 pounds, referred to LB. LP is the symbol for pound, which is not an SI unit to measure weight anyway. And the question says, what is the mass in milligrams? And he's given you that 1 pound is 453.6 grams. It's almost half kilo. So how do we do this question here? So here we go. Before the lecture, I organize my work as follows. Example 1.6, we have 0.0833 pounds, and we need to change this to milligrams. We are giving a conversion factor, which is 1 pound is equal to 453.6 grams. Okay, so basically then I need to go from pound to grams to milligrams. Okay, so that's easy. I'm gonna get what I'm given, okay, which is this number 0.80833 pound. In unit analysis or in dimension analysis, I always multiply. Don't worry about division here, because division will come by itself. So here I'm gonna change this to grams first. It does make sense that I put pound in the bottom and grams in the top. I'm gonna ask myself, does 1 gram equal 1 pound? No. 1 pound is equal to 453.6 grams. Okay, that's nice. The pounds just went away with pounds here. They're shaking hands and going home. Am I done? No, I need to go to milligrams. So one more. Grams in the bottom, milligrams in the top. I think you got it now, okay? This is beautiful. And 1 gram is 1,000 milligrams. See, it's just working itself out. The grams goes with the gram. And now, there's nothing left, just milligrams and the numbers. So basically you multiply the 0.833 times 1,000, and that will give you 833 milligrams, which is the correct answer. The only thing left that you want to think about the way you write the number, or the formula of the number, the format of the number. Here you have, how many? You have 3 significant figures. I think you agree that here we have 3 significant figures. For sure they're not 5, because zeros to the right, to the left, they don't count. Here how many? We have 4 significant figures. This is an exact number, so you don't worry about it. So the battle is between 4 or 3 here. 4 or 3. Of course, this is multiplication, so we go with the lowest number of significant figures, and therefore the final answer should have only 833 milligrams. So we wrote this in the correct way. One more question. 1.7, a liquid helium storage tank has a volume of 275 liters. And what is its volume in meter cube? Consider yourself working in a company or a factory, and you want to convert this. And this is a daily exercise that you want to do when you are in a working place. You work with units all the time. So 275 liters, what is that in meter cube? Okay, let's think about it. That's example 1.7 again. 275 liters meter cube. Well, let's recall the conversion factors. I know that 1 liter is equal 1,000 milliliter in other words centimeter cube. That's not helping here, because I know that also 1 meter cube is how many liters? It's 1,000 liters, okay? 1 meter cube is 1,000 liters, or 1 million milliliter. So we need this here. So this question is pretty straightforward. It's only one conversion. So I would say 275 liter multiplied liter down, meter cube up. 1 meter cube will be this. So that will be 0.275 meter cube. Super easy. 3 significant figures, 3 significant figures. We are fantastic. Last question in this chapter is: liquid nitrogen is obtained from liquefied air and is used to prepare frozen goods. Low temperature research. This is a statement that has nothing to do with the question. It's just to confuse you, or just to provide you with the general information. The density of the liquid at boiling point, which is minus 186 or 77 Kelvin, is 0.08 kilogram per centimeter cube. Convert this density to units of kilogram per meter cube. So basically the question is asking to convert the density from one unit to another. All the other informations, including the temperature in the brackets here, I don't think it has to do with the question. So it looks like this is a complicated question, but basically it's just asking you to, or she's asking you, we don't know who is the author of the book. She might be she or he. So we just need to convert the densities here between gram per centimeter cube to kilogram per meter cube. So again, I brought this to my whiteboard. I don't know why I keep saying blackboard. It is whiteboard. So we have a 0.08 gram per mil to kilogram per meter cube. Okay, so now I know that 1 kilogram is 1,000 grams, but I want to go from meter cube into milliliter. That's a lot to convert. Maybe I can go from meter cube to liter, and then from liter to milliliter. Okay, so let's do that in 2 steps. So that's a lot of. This is actually. It's a lengthy question because you have to do a lot of conversions here. You start with 0.808 gram per mil. Let's get rid of the gram first. So that's gram is in the bottom, kilogram in the top. 1 kilogram is 1,000 grams. And then I want to change this milliliter to liter. So I'm going to bring this in the top, liter in the bottom. So 1 liter is 1,000 milliliter. And again, I want to reach meter cube. So I want to put liter in the top, meter cube in the bottom. So 1 meter cube is 1,000 liters. Let's see if this works, okay? Or if we made any mistakes. The milliliter will go with milliliter there. Liter will go with the liter, and meter cube, what else? Gram will go with the grams. And we are left with kilogram per meter cube. This is beautiful. So it worked out. So the answer will be kilogram per meter cube. And so basically what you do here, okay, let's say that this 1,000 will go with this 1,000 as well. So you are just multiplying this 0.803 times 1,000, and that will give you 808 kilogram per meter cube. So, okay, so we solved the question. 3 significant figures. 3 significant figures. Life is beautiful. And notice here that the density in a gram per mil is not actually the same as kilogram per meter cube, as I said maybe at one point in this lecture. So by this, this chapter is done, chapter 1. So thank you so much for listening, and I hope that you can have the chance to see some videos here and solve some problems. Please do the problems in the textbook, the practice exercises, do the online ones, and as well do the exercises at the end of the chapter, please. There are some problems at the end of the chapter. They are beautiful problems, so find some time to practice as much as you can for this chapter. So thank you so much for listening, and have a great day.